Good afternoon, everybody. Happy Friday. Welcome to lecture. So we are going to have a survey question here first that we'll look at, and then we'll go to benzene nomenclature and more benzene ring, aromatic ring kinds of chemistry. So this is one that deals with Diels-Alder and exo-endo type questions. So you had these two molecules that you were given as starting materials. There's a diene here, and you can tell because it goes double bond, single bond, double bond, and it happens to be connected together into a fused ring system. There's a bridging group, or it's a ring basically, and there's a bridging group there. So that's going to turn up in the product. Then we have a dienophile here, and the thing about the dienophile is it's a cis dienophile. It has two groups attached to the dienophile, C double bond C, that's going to be forming the sigma bonds and making the cyclohexene ring. So when you line these things up, you get the six-membered ring, and remember the new bonds are right here and here. And then all the stuff on the left side of this molecule came from the diene. So if I was to sort of cut this in half and show you where everything came from, everything on the left side of that squiggly line came from the diene. And you got to make sure the methyl groups on the diene get in the correct spot in the product. And so they are at the, not at the ends of the diene, but kind of in the middle of the diene. So that's where they turn up in the product. And then the dienophile is incorporated over here, and the two things you need to make sure of is that you get the cis orientation in the dienophile. So here, this ester group and that ester group are both pointing down towards the bottom of the board. That's a cis type arrangement, and of the two cis type arrangements, this is the best one because this one has these two groups in an endo position. They were underneath the diene during the Diels-Alder reaction, and that's better because they have these p orbitals that can overlap with the p orbitals in the diene, and then they get some of the secondary orbital overlap. So that makes the endo product the major product. And that was option C in the question. There's also an option that showed the exo product, which has the hydrogens and the esters switched. That's also a possible product that does form to some extent, but it's less important because the exo doesn't have this secondary orbital overlap, so it's not as common, it doesn't happen as frequently, and that's a minor product. This is the major product. And that was C, and people did well on it. I looked at the statistics, and it was overwhelmingly the favorite answer, so that's good. So it leads me to believe most people are kind of understanding this pretty well, so that's really good. Glad to hear that. So if you have any questions about Diels-Alder, you can ask me in office hours, catch me in lab, whenever. But we're moving on now, as we did last time, and we're going to talk about aromatic ring chemistry. So what we finished up with last time was a discussion of how to name benzene rings. And we talked about a lot of basics, and we're going to continue that a little bit, and then we're going to move on to some other more interesting things. But I wanted to first introduce you to a group that you probably haven't seen before. This is called a nitro group. It has, the squiggle line here indicates that that's where it's connected to something else, and the nitro group has a nitrogen that's got two oxygens bonded to it. One of the nitrogen oxygens is a double bond. The other nitrogen-oxygen bond's a single bond. Nitrogen has a formal positive charge, and then one of the two oxygens, the one that's making the single bond, that has a formal negative charge. And there's a resonance structure where this minus charge is shared with the other oxygen. But since nitrogen can only make 4 bonds, you can't ever have a neutral nitrogen in the nitro group. It's always positively charged. So that's the full Lewis structure description of it. And you might see it in structures in homework assignments where it's just written as NO2, which is just the chemical formula. It's an abbreviation. It's a condensed structural formula for nitro. So just wanted to call your attention to that because you will see it in naming questions. And in the next chapter, not until after the exam, we won't be getting to that one, but there's a lot of nitrochemistry that involves aromatic rings in an upcoming chapter. So it's an important group to get a handle on. Okay, so let's look at an example where we've got one of those. And we'll see if we can decode what the answer ought to be to the name of this molecule. So here's a benzene ring that's got some groups on it. And we need to figure out how to approach naming it. So we need to look for one of those root names that we learned last time and see if there's one of those in there. And there is in this case. And so if you go back in your notes and you look, what are these special substituents where the parent then has a special name, and one of them is aniline. So this is a molecule that has an aniline as its parent name. So root name or parent name is aniline. So we need to figure out how to name this as a substituted aniline. And when you have a root name like this, the position that the root substituent occupies is given a 1 by default. And then you have to turn around the ring to give low numbers to the other groups. And that would be going counterclockwise in this case. And then you get a 2 here, a 3 here, and a 4 there. So we've got an aniline that has a nitro in the 2 position and a chloro in the 4 position. And then you do alphabetically list the names of the groups out in front of the parent name, and since Cl for chloro is before N for nitro, that substituent comes first. So it goes 4-chloro, and then dash, and then 2-nitro, and then you just say aniline with no need to specify that this root group is in the 1 position, because everybody knows that, or it's by definition it's there. So 4-chloro 2-nitroaniline. That is how you name that compound. So that's one more example. One more example that I want to show you is that sometimes you get benzene rings as substituents. So if you see a complicated benzene ring and it's got another benzene ring on it that's a substituent, you can name that as a substituent, and it's called a phenyl group. So I'm going to show you what that looks like, and then we'll look at an example of it. So when you have this kind of a situation, when you have an aromatic ring that's a group on a larger, more complicated molecule, this is called a phenyl group. And it's important to be sensitive to the vowel here. That's a Y. When you see phenyl with a Y, that means you're talking about a benzene ring that's a substituent. It's a very close, closely spelled version or word that really is very close to phenol. So don't get the two mixed up though. So you've got phenyl group, and then this molecule, remember, is called phenol. So, I mean, they look very, very similar, and if you're not careful, you might accidentally mix them up, but try not to. And so you can name a molecule like this, and here is an example of a molecule that's got a phenyl group on it, but also has a phenol. I'll just put a methyl over here to make it, well, I'm not going to use a methyl because methyl is, you get into, you have to worry about, is it a toluene or is it a phenol? Okay, so here's a molecule. We've got to figure out how to name this thing. And if you see it, I mean, it looks kind of big, but don't panic if you see this. Just go through the protocol that you would normally do and try to find a root substituent. And there is one here. It is got this phenol. So it's a phenol. That's the parent name, the root name. And it's got groups on it, and that's the number 1 position. And then there's 2 and 3 and 4, and I'm numbering it that way so that I can give the lowest numbers to the groups. So then you put them out in front of the parent name phenol, these groups, with their numbers in alphabetical order. And so E for ethyl comes before P for phenyl. So you get 2-ethyl, 4-phenyl, phenol. Phenol. I picked this one on purpose because it's kind of the most confusing example I can think of. So if you can understand this, you're doing fine. So anyway, just get used to seeing benzene ring as a substituent, because sometimes that happens. And that is all I have to say about nomenclature, unless you have any questions. Anything you don't understand about nomenclature that you'd like to know? There's always more to know about nomenclature, but there's a point at which you have to say, well, I know enough, and I don't want to spend any more time on it. And that's where I think we are at. So I would love to get back now to talking about What makes benzene special? It is like I said, it's kind of a weird molecule. It's super, super stable. I mean, much more stable than you would predict based on what you know about alkenes. And we studied alkenes last semester in one of the chapters towards the end of Organic 1. And we saw them doing a lot of things. We saw them things adding to double bonds of alkenes. Benzene rings don't do that. Even though they've got carbon-carbon double bonds, they appear to have carbon-carbon double bonds in them. They're really different. They're not alkene-like at all. Really, they behave very differently. So I'm going to show you a series of hydrogenation experiments that try to shine some light on this and explain or help you understand what this stability is all about. So here is, well, I'll just put a title up here first. I'll call this benzene is unusually stable. And here are some experiments that help try to highlight that. So here's a reference hydrogenation experiment. If you go with a cyclohexene and you put in hydrogen and palladium on carbon, you'll add hydrogen across the double bond of the alkene. And you'll get some heat out because it's an exothermic reaction. And the amount of heat that comes out, let's say here plus heat, the delta H for this reaction, that's the amount of heat that you measure coming out. You could figure that out by just measuring how much does the reaction heat up. It's 120 kilojoules per mole, which by itself doesn't really help you a whole lot. But let's look at some other molecules and see how they compare. Here's another reference molecule. This one has 2 double bonds in it. So if you put this in with 2 hydrogen molecules, palladium on carbon, and you add hydrogen across both of the double bonds, you'd get out cyclohexane and some heat. And so let's look at a couple possibilities. Here's delta H. I'll call it predicted, which is what you'd predict if there was no such thing as resonance. And I've been telling you resonance stabilizes alkene double bond dienes, for example. We saw that in the previous chapter. And we measured a difference in delta H for a conjugated diene. There was some missing heat, basically, and that heat was what we call the resonance stabilization. So the predicted here would be 2 times that, because if it's just about a double bond inside of a 6-membered ring, and there's 2 of them here, maybe it's just 2 times, I should go back here, it's minus 120. Heat comes out of this reaction, so that I should have a minus charge here. So 2 times minus 120 kilojoules per mole. So, you know, maybe minus 240 kilojoules per mole. That seems logical. And then if you go in and you do the experiment, I'll call it experimental. The heat that comes out of this reaction in reality is 232. Just make sure I get this right. Yep, 232. Kilojoules per mole. So they don't exactly agree with each other. The conjugation provides some stability. So the difference here is resonance stabilization. Is equal to 8 kilojoules per mole. So the diene is a little more stable because it has its double bonds conjugated. They're able to share electron density through the pi system of overlapping p orbitals throughout the system. And that helps a little bit. It stabilizes at 8 out of 200, and compared to 240, it's 232. All right. Nothing you're going to go wow over probably, but it does make a difference. All right, let's take a look at benzene now. So we take this idea one step further and say, well, let's see what happens if we take a six-membered ring and we get 3 of these double bonds in it. And you put 3 hydrogens in it, you put the catalyst in, palladium on carbon, and you get out a cyclohexane plus some heat. Let's predict what we would get here. So delta H predicted, and that'd be a prediction based on having no impact from conjugation. If there was no such thing as conjugation, it was just about individual alkenes in a 6-membered ring getting hydrogenated, how much would you get out? Well, we're going to do 2 times this 120 value that we got for cyclohexene. So, or 3 times that. So 3 times minus 120 kilojoules per mole. That was the value of 1 double bond in a system that only had just that in it. Then we'd get minus 360 kilojoules per mole. Well, the delta H experimental, what you get when you actually measure it, is equal to minus 208 kilojoules per mole. Audible gasps. Wow. There you go. I was looking for a wow. Okay, so the difference here is really dramatic, and so stabilization here is 152 kilojoules per mole. So it shoots way up. There is something really special about having a complete circle of conjugation. This is a situation where the electrons in the pi system are able to circulate in a donut pattern. So they're completely, it's a really kind of extreme conjugation. And this is such a big difference that we call this this phenomenon aromaticity. It's this special stabilization. It's really like extreme conjugation, basically. It's really, it's a big difference. And benzene is the most common, most important example of a conjugated molecule that has this special stabilization, but it's not the only one. There are a lot of conjugated molecules out there that are really important. Not conjugate, aromatic molecules that are out there that are really important. So we need to learn about what makes them tick. Why are they aromatic? What traits do they share? How do you know, if you look at a ring, whether it's going to be aromatic or non-aromatic, or there's even a thing called anti-aromaticity, which is an especially unstable ring. And so we're going to talk about all these things next. But before I go on, I just want to emphasize that benzene isn't like other molecules in terms of its reactivity. You can't do a lot of the same reactions that you would normally do with an alkene. It's really resistant to that. So you can see that stability. This is why a benzene ring is so common in nature. If you go look at natural molecules, they've got a lot of these benzene rings in them, because when molecules come together, atoms come together to make a molecule like this, they get a special stability. So it's a theme that keeps repeating itself over and over again. And aromatic rings of other types are also really important in nature, in pharmaceuticals, in agrochemicals, in personal care products, in nutrition, and they're just all over the place. So we're going to talk about aromatic rings now. And we're going to look at some criteria for aromaticity. What makes a molecule aromatic? Benzene's our first example, the most important example, but there are other molecules out there that share this trait. So this is going to be some rules for aromaticity. And if other molecules follow these rules, they will also be aromatic and they'll have this special stability. So the big thing is, this is a general phenomenon, rules for aromaticity. Aromaticity is it's a general phenomenon. And other molecules besides benzene can be aromatic. Other molecules besides benzene can be aromatic if they follow this set of rules that we're going to lay out here. So rule number one, it has to be a ring. To be aromatic, the molecule must be cyclic. It's a really important feature. If the molecule isn't a ring, it can't be aromatic. It's got to be tied into a ring so that you mimic benzene's circular structure with its overlapping p orbitals and electrons shared in a circle. Second thing is the molecule must be flat. To allow p orbitals to overlap. So that's going to be important when we start looking at big molecules, like bigger molecules than benzene that have some flexibility and can bend in various ways to either be flat, planar, or puckered out of planarity. Yeah, we're going to talk about puckered molecules a lot. Kind of a fun word. All right, the ring must be fully conjugated. The ring must be fully conjugated. In other words, every atom on the ring has to have a p orbital that's overlapping with a neighbor p orbital. Ring must be fully conjugated. Each atom must have a p orbital, because that's what conjugation is. It's like adjacent atoms with adjacent p orbitals that can overlap. So that's got to be a complete circuit, basically. And then the last thing, and the most obscure thing, and the hardest thing probably to digest at first, is going to be there's certain patterns of electrons that you have to have. So there must be for n plus 2 pi electrons in the ring. And this is n, so to understand this equation, think of n as n has to be a whole number. N must be a whole number. It can't be like a fraction or a decimal. So think of it, it's got to be, n has got to be equal to 0 or 1 or 2 or 3, like that. It can't be 1.5, or it can't be 0.75. So if you count up the pi electrons in a molecule and they fit this formula where you can find an n value that is a counting value, then that's a type of electron configuration that leads to aromaticity. Let's go through a few examples to just explain what this equation means and how you can use it. So let's look at some values of pi electrons. And we'll learn how to count pi electrons. We'll spend a lot of time on this, but let's look at some scenarios. Number of pi electrons. If you're a molecule and you have 2 pi electrons, well, let's say 0. Let's do even values. 0, 2, 4, 6, 8, 10, 12, and you can go on and on like this. Can you find a value of n that fits this one? Like, in other words, is there some, so what we're trying to do here is we're mapping 4n plus 2 onto these values. There is no n value you can use here that would really get you this one, because you're always going to have 2 here. So maybe what I should do is I'll just erase this as 0. Let's look at the values that have positive numbers of pi electrons, even. So 2, can you find a value of n that makes this equation true? 0, right. If you took, if you had 2 pi electrons, if x here were 2 and you made that a 0, then it would work. So this one is, this one's going to be an aromatic. We'll predict that's an aromatic complement of pi electrons. So if you have 4n plus 2 is what you're looking for, then that's going to be an aromatic type arrangement. And maybe what I'll do is I'll put that aromatic label over here and just say that one's aromatic. All right, what about 4? Is there any counting number that if x were equal to 4 that you could stick into here that would work? No, I mean, there's a number, you could 1/2, but you're not allowed to do that with this equation. So 4 doesn't work. 4 is not one of the complements of pi electrons that leads to aromaticity. In fact, it fits a different rule. It's an even multiple of 4. So what we're going to do is we're going to learn to look for pi systems that fit either 4n plus 2 or 4n, where basically the pi electrons are an even multiple of 4. So 4 is definitely an even multiple of 4 if n is equal to 1. So these are going to be different. And in fact, these are going to be what we lead to anti-aromatic type systems. That's a complement of electrons that leads to a situation called anti-aromaticity, which is a special instability. If we go back to 6, I can find a value of n that, if I put 6 in here, that works for this. If n is equal to 1, then it's 4 plus 2 is equal to 6. That works. So this is another complement of electrons that's aromatic. And by the way, that's good news, because benzene has 6 pi electrons. So if we're going to, for this to make sense, that would definitely have to be aromatic. 8 is a multiple of 4n, so that leads to anti-aromaticity. 10 is a multiple of 4n plus 2, where n is equal to 2. So this is another one that leads to aromatic. And then 12 is anti-aromatic because it's an even multiple of 4. 4 times 3 is 12. And so you can go down like this, and basically any even number of pi electrons is either going to be associated with an aromatic type situation or something called anti-aromatic. So that's what the n plus 2 rule means, and this 4n rule. An odd number of pi electrons leads to neither of these situations. So I'm going to now explain a little bit about other situations. So we've got over here, just flash back to this set of rules over here that we talked about before. There are all these rules for aromaticity. If the molecule follows all of these rules, it will be aromatic. Molecules that follow rules 1 through 4 are aromatic and especially stable. just like benzene. Benzene's got an unusual stability. Any molecule that mimics benzene's properties would also be especially stable and aromatic. Then what happens in other situations, molecules that follow rules 1 through 3, but have 4 n-pi electrons, are called anti-aromatic. And very unstable. So let's just flash back to the rules about aromaticity and look at rules 1 through 3 again. So anti-aromatic compounds are very similar to aromatics in a lot of ways. They're rings, they must be flat, they have to be fully conjugated, but instead of 4n plus 2 pi electrons, they have 4n pi electrons, and then they have this special instability. It's kind of like the evil twin of aromaticity. You know, if they were superheroes, it'd be the evil twin, I guess. Okay, so if that makes any sense at all, I don't know. All right, and then let's just talk about one other situation. Is every other ring is just what's called non-aromatic. Every other ring is what we call non-aromatic. It's not anti-aromatic, it's just non-aromatic, which means it isn't especially stable, isn't especially unstable, it's just kind of normal. Doesn't have anything weird going on with its stability. Every other ring is non-aromatic and has no special stability or instability. So it's kind of a special set of circumstances that you have to be is if your molecule, if you're going to be aromatic or anti-aromatic. Most molecules are just non-aromatic because they fail one of the rules. In order for it to be anti-aromatic or aromatic, they have to like follow all the rules. And so what we're going to do now is look at a series of molecules to see when the different situations happen: aromatic, anti-aromatic, or just non-aromatic. 3 different possibilities. But before I go on, are there any questions about these kind of 3 situations? You'll never look at organic rings the same way again, probably. All right, let's take a look at some examples of molecules that fit into these different classifications and how you can know. We know about benzene, so I won't go through that one. But let's go through some examples that are kind of closely related to benzene. Let's look at this one. This is called cyclobutadiene. Okay, 4-membered ring with 2 double bonds in it. Let's predict, test it out for the rules. So rule number 1 is it a ring? And sure, it's a ring. That's a pretty easy one to spot. It is a ring. Okay, so it's criteria number 1 fits. Is it flat? Small rings like this that have all sp2 hybridized atoms really have to be flat. They're not flexible enough to bend out of planarity. So what I want to do is put down kind of a rule you can follow. So rings that have all sp2 atoms and have between 3 and 6 atoms in the ring will always be flat. Just because that's the nature of the sp2 hybridized atom, is it's trigonal planar. So when you hook a bunch of them together, they tend to like to be in a plane. The only way you can get out of being a planar molecule with sp2 hybridized atoms is if you bend and pucker. And when you start to get to ring sizes bigger than 6, then they start to become large enough that they're flexible enough to do that. So I want to put a rule about that up here too. Rings with 7 or more atoms in them are flexible enough to be either planar, meaning flat, or puckered. And that would be not flat. So I want to show you an example with an 8-membered ring, just because this is another fun one to talk about. So here is a molecule called cyclooctatetraene, and it looks like a stop sign. It's an octagon. Okay, so this one, because of its size, would be flat. It's also, it is a ring. So if I do these checks on here, it is a ring, it is flat. Is it fully conjugated? Well, it's got a p orbital here, p orbital there, p there, and p there. So it's a full ring of p orbitals. So yeah, it's fully conjugated. So I'm going to put fully conjugated. And for pi electrons, it's got 4. You count 2 for every pi bond. So this goes 2, 4. So it has 4 n. Well, maybe what I'll just say is 4 pi electrons. That's a complement that's associated with anti-aromaticity. So this is an example of an anti-aromatic molecule. It's very unstable. This molecule is really hard to access. It's not like you can put it in a bottle and store it on a shelf. People have tried to make this thing, but as soon as they make it, it usually likes to react right away. So you have to use special tricks to try to isolate it. Usually people try to make it in the gas phase where it isn't near any other molecules and can't react with any other molecule. And then they can study it for a little while, like by mass spectrometry. But otherwise, it's really tough. This molecule has a tortured existence. It really doesn't want to be like this. And any chance it gets, it'll do something else. Okay, let's look at this one. This one is a ring. Is it flat? I'm going to put a question mark next to it because it could be flat or it could be puckered. Let me show you. Here's a model of cyclooctatetraene where I've got the double bonds indicated with these curved things that are representing the p orbitals overlapping. Okay, it can be, if you look at it on edge, it can be flat, but it can also do this. It can also do that. So there, now it's puckered. So it can choose. Which does it want to be? Does it want to be flat? Does it want to be puckered? Flat, puckered, flat, puckered. It must have a favorite way to exist. Favorite conformation, that's like, where is it most comfortable? So let's think about this. It is fully conjugated. How about pi electrons? How many pi electrons does it have? 8. Yeah, you count 2, 4, 6, 8. So 8 pi electrons, that's a 4n type system. So here's the deal. When this molecule is flat, it is anti-aromatic. This molecule over here is anti-aromatic when flat. Just a reminder, that's very unstable. This molecule hates to be flat. It does not like that conformation because it's terribly, terribly high in energy. So it will do what it can to avoid that. So what it does is it puckers. It puckers out of planarity to become non-aromatic. Because basically, by avoiding being flat, it no longer is fully conjugated. That ring of electrons is broken, and so it isn't anti-aromatic anymore. It's just non-aromatic. Non-aromatic is better than being anti-aromatic. The hierarchy of energy is aromatic is the best. That's the lowest energy. Non-aromatic is just kind of normal, and anti-aromatic is way up high. So if you're a molecule, what you want to do is adopt the conformation that gives you the best energy state, the lowest possible energy position. They like to be comfortable. That's what they do. I mean, they'll arrange themselves in whatever the best arrangement is. And for this molecule, cyclooctatetraene, flat is bad. Puckered is better because it doesn't suffer from that big energy penalty of being anti-aromatic. So we'll take a look at this with other molecules to try to ask questions about, would you predict this molecule will be flat? And so we'll have a little discussion about that now, and I'll draw some structures on the board and we can predict. And it's mostly about counting pi electrons. So let's look at an example of this. Okay, I want to draw for you now a molecule that has this structure. It's kind of an interesting polygon, and it has alternating double single bonds. So double bond, single bond, double bond, single bond, double bond, single bond, all throughout. If you count the number of atoms, there are 14 atoms. And the name of this molecule and molecules that are similar to it is, they're called annulenes, and they have the number of atoms that they have in front of it, and then it goes annulene. So 14 annulene. So it's certainly big enough to be either flat or puckered. It could adopt either conformation. So what would it like to be? How would it like to be? It's a ring. It's fully conjugated when it's flat. It has a certain number of pi electrons. Let's count them. I'm going to start counting up here, and the big thing is just make sure you know where you're at. So I'm going to just put a little mark here so I remember where I started. 2, 4, 6, 8, 10, 12, 14. It has 14 pi electrons. Does that fit 4n plus 2 or 4n? Can we find a value for n that makes this true? 6, yeah. So 6 times 4 is, no wait, that's not right. 3. 3 times 4 is 12 plus 2 is 14. So yes, it works when n is equal to 3. So in other words, this is a 4n plus 2 system. This molecule, when it's flat, would be aromatic. Aromatic when flat. This is the favored conformation. It flat, because being flat gives it this special energy stability bonus. If it puckers, it would just be non-aromatic, which is higher in energy. So it picks the lower energy option, which is flat for this molecule. All right, let's look at another one. And you'll start to see how the game works, basically. It's mostly about counting pi electrons. You got to make sure that it fits all the other rules too. But once it does, and you just count the pi electrons, figure out, does it fit the 4n plus 2 rule? Does it fit the 4n rule? And that'll determine whether it wants to be flat or puckered. So here's another example. These large polygons aren't real easy to draw, so if you're struggling a little bit with it, don't worry. All right, what do we have here? It is a ring. Every atom is sp2 hybridized. Every atom has a p orbital. It would be fully conjugated if it were flat. So the big question is does it want to be flat? Does it want to be puckered? And the answer is dependent on the number of pi electrons. So if we start counting them, if I start counting here and I go 2, 4, 6, 8, 10, 12, 12 pi electrons, this is a multiple of 4n. So this is one that if it were flat, it would be anti-aromatic. Anti-aromatic when flat. That's bad. It likes to pucker. To be just non-aromatic. So puckered is the key conformation for this one. This one would want to be not flat, because it's just a better energy situation for it. So that's the way these things go. And you'll see a bunch of questions like this, predicting, is this molecule flat or is it puckered? All right, let's take a look at another one. Sometimes you'll see questions posed to you like this. It'll give you a ring and it'll ask you, predict whether this would be a flat or puckered molecule. Then you have to go through the exercise like we've been doing, where you count the pi electrons and you determine that it's fully conjugated, and then whichever conformation gives it the lowest energy. Like if being flat makes it aromatic, then it wants to be flat. If being flat makes it anti-aromatic, then it wants to be puckered. So basically that's one version of a question. Another version of a question that you might get is that you might see a ring and it might tell you, assume this ring is flat. What would it be? Would it be anti-aromatic or aromatic? So just read the directions and you'll know how to answer the question. Okay, so here's a question I wanted to ask you about. You might see this and it might be, is it aromatic, non-aromatic, or anti-aromatic? You might have to circle one of the three. This is a real common kind of question. So let's see, is it a ring? Yes, it is a ring. Is it flat? Well, it could be flat. This is a 7-membered ring. It could be puckered or it could be flat, depending on what gives it the best energy advantage. Is it fully conjugated? No, good. People are catching this. There is a problem here, and and it was subtle because I didn't put the H's on here, but this is a carbon that's sp3. And that's a break in the conjugation. This is not a fully conjugated ring. There's a sp3 atom here that does not have a p orbital, so the communication isn't all the way around the ring. There's like a horseshoe of conjugation in this molecule, but a break right there. So this molecule is not fully conjugated. Due to sp3 atom that has no p orbital on it. So this one is just by default non-aromatic. It doesn't matter how many pi electrons it has. Any non-conjugated molecule is always going to just be non-aromatic. So it doesn't have any special stability or instability. It has a little stability because it is conjugated, but it isn't like aromaticity level kind of stabilization. You get a little bit of stabilization from conjugation, but mostly it's just a normal molecule. It's not really stable because it's not aromatic. Non-aromatic for this one is the answer. So look for that. And just make sure before you start counting pi electrons that you know you've got a fully conjugated ring or not. All right, let's look at some other kinds of molecules. The thing about aromatics is because they're especially stable, you see them all over the place and there's a lot of variations. So there's a lot of variety in aromatic rings. And I want to show you that sometimes you get more than one ring in a molecule and how to count those pi electrons. So here is a real common molecule. You've probably smelled this one at some point. It's called naphthalene. Anybody know where naphthalene turns up in household products? Mothballs, yeah. So if you've ever smelled mothballs, this is apparently moths don't like them. I don't know. Anyway, but it's got some rings in it. But how do you handle it? There's a ring here and a ring there, and they're sharing some electrons. So what you do is you consider the whole ring system. Don't like look at the left one and then the right one, but consider it all together. So if we're going to count pi electrons in this system, first of all, it is a ring. It's like a series of rings, but they're fused, so it's a complete ring. It is fully conjugated. There's a p orbital at every single juncture in this ring system. And it would be flat because 6-membered rings typically are. And how many pi electrons? Well, it's got 2, 4, 6, 8, 10. 10 pi electrons. This is a 4n plus 2 system, and it's going to be aromatic. By the way, aromatic, where the word came from is before people really knew much about structure, they knew that aromatic molecules had a certain smell to them, or a lot of them did, and so that was originally how they were classified, based on molecules that smelled a certain way. Since we've gotten a better understanding of structure, we know it's related to these pi electrons and the rings and the conjugation and all of that, but the name stuck. So we still call them aromatic rings. It doesn't really matter how they smell. They're related by structure and bonding more so than by smell. But anyway, the name is like a historical kind of artifact, I would say. So if you're curious about that, that's when we say aromaticity, we're mostly talking about energy and stability and not so much about smell. Okay, let's look at another one. This one's called anthracene. And it's a series of 3 fused rings. And if you count up the pi electrons, there's 2, 4, 6, 8, 10, 12, 14. 14 pi electrons. That fits 4n plus 2, where n is equal to 3. And so this would be aromatic. So there's a lot of examples like this. There's many types of molecules where you have multiple benzene rings that are fused together in interesting ways. But the way you handle them is the way you handle these, where you count the pi electrons in the whole system. Okay, what about other atoms other than carbon? So we focused on carbon now, but there's a lot of other interesting atoms out there. What happens when you have a nitrogen in your molecule, for example? And the answer is it depends on exactly how the nitrogen is incorporated. But here's an example of a heterocycle. So we're going to start looking at heterocycles. We'll call them heterocyclic rings. The heterocyclic means that there's a heteroatom in them. That's an atom that's not carbon. Could be nitrogen, could be oxygen, could be sulfur. But something other than carbon is making up the ring. So what would be going on with this molecule? This one's called pyridine. And so to really get a handle on this, you need to know something about the bonding in it. You got to be able to account for all the electrons that the nitrogen has around it. And you could draw a molecular orbital bonding picture for this molecule that looks like this. I'm going to draw it on its side with an edge-on view and draw p orbitals on every one of the atoms. And I know that nitrogen is sp2 hybridized because it's got a double bond in it. It's got 3 electron groups. This is the structure of pyridine. It has a lone pair that's in an sp2 hybridized orbital. And then the p orbitals on all of these atoms, they're overlapping. So there's overlap here, there's overlap here, there's overlap here and there. Basically, it's like benzene, very similar to benzene. The upper lobes of the p orbitals overlap and make a donut, and the lower lobes of the p overlap and make a donut. And there are 6 pi electrons in that pi system. I'm counting 2 for every double bond here. I'm going 2, 4, 6. So in this pi system, there's 1, 2, 3, 4, 5, 6, and I'm just drawing them in places to just keep track of them. It's not like they're stuck in those spots. They're smeared out over the whole pi system. But here's the thing. The lone pair on the nitrogen is not in that pi system. It's poking out of it. It's orthogonal, 90-degree angle to it. So these are not pi electrons. And when you're counting electrons to figure out, does this have 4n plus 2 pi electrons, you leave these out because they're not in p orbitals. They're in an sp2 orbital that's pointing outside of the pi system. So this molecule pyridine has 2, 4, 6 pi electrons. And it's aromatic. And what people have found is that these electrons are basic, meaning that they will be donated to a proton. We're going to talk more about that next time. But the molecule is okay giving them away to a proton because it doesn't impact its aromaticity. If it shares that pair of electrons with an acid, it's still an aromatic ring. We're going to look at some other rings where it doesn't work that way. In fact, the molecule might not want to give up its lone pair because that would cause it to lose its aromatic character. So we're going to see that next time. So have a good weekend.